Cool. So today we're going to be talking about scaling blockchains, and this can be a very complex topic in the space. There's a lot of cutting edge stuff going on right now. There's a lot of different proposals as to how to do it. So this will be kind of a survey of a few that are going to be pretty detailed, some of which I'll be kind of skipping over because we just don't have like the full on time to go over everything. So let's talk about the status quo a bit. Right now, we know that Bitcoin is pretty slow. Maybe takes like a couple hours to see like our transactions get inside a block. It's about 7 transactions per second on average. Ethereum, a little higher, 10, sometimes 15. And then you can compare, usually this comparison is here where you look at Visa's average, you see it's 4,000 transactions per second. You feel a little bad about the blockchain space, and then you maybe think of ways to contemplate that, either by joining the scaling research team or leaving the space completely. So one way to look at scaling is you can define something known as the effective throughput, and that is basically the maximum block size divided by the block interval. And basically the effective throughput is, it's an upper bound. Right, it's not necessarily what happens on average. It's an upper bound for how fast you can confirm blocks. So the block interval being that the time takes to confirm a block, and one of the questions that we often ask is, can we reach this? Can we reach this idealistic performance of 56,000 transactions per second? And the answer is maybe, and that's what we're going to be talking about today. So there's been a lot of debates in the current blockchain space. Last year mostly, a lot of this debate went on about block size and how many transactions you should be putting inside a block. This form of scaling is known as reparameterizing because you're simply just changing system variables inside the blockchain clients. This, though, is not quite as scalable as other solutions out there, mainly because changing variables can cause issues, and that includes messing with the effective throughput and also the accessibility of the network. You have to make a compromise. You can have a bunch of supercomputers running the Bitcoin network, sure, but is it then like a decentralized currency that's being run on multiple nodes at that point? It'll run really fast, but you're then kind of compromising what a blockchain is. And if you really just want speed, you should be using databases, right? Because databases have all these amazing optimizations you can do on a very centralized point, and even distributed databases too. So some guidelines that have been kind of researched and proposed is usually block size should not exceed 4 megabytes, given today's 10-minute average block interval. And that'll basically be 27 transactions per second maximum with a 4 megabyte block size. And the block interval should not be smaller than 12 seconds, which is about the block interval for Ethereum's Ghost protocol. And these upper bounds have kind of been researched on as to why they're here. And this is why there's like a huge debate on this, because some people kind of refuse to acknowledge that there's this research out here that shows that you will compromise the decentralization of the network by increasing the block size past a certain point. And some people just refuse to read the research. So that's why you have stuff like Bitcoin Cash and Bitcoin. So the max throughput right now in Bitcoin is about 3 to 7 transactions per second, right? And that is constrained by the block size and the inter-block time. There's also basically some latency where it takes about 10 minutes to confirm that entire those set of transactions for that block. And there's also bootstrap time, which is also a scalability bottleneck because the blockchain takes about 4 days to download on average. Maybe some of you who tried to also sync Geth noticed that it took quite a while to sync it if you ran it on full mode. Another I guess a variable that we look at is the cost per confirmed transaction, And that's basically the cost in USD for the resources consumed by the entire Bitcoin network in order for it to run, in order for it to actually confirm a single transaction in this case. So what does the cost per confirmed transaction include? It includes mining, how much is expended cost-wise by generating the proof of work for each block. What's the cost per block? You have transaction validation. What is the cost of computation necessary to do essentially a Merkle proof? And the bandwidth, which essentially the cost of network resources required to receive and transmit transactions, block, and metadata. So that costs money because you need internet infrastructure and you got to pay for it. Storage, the cost of storing all currently spendable transactions, which is necessary for miners in full nodes to perform transaction validation, and of storing the blockchain's much larger historical data. So you can imagine this can be like pretty expensive because the blockchain is now on order of magnitudes, hundreds of gigabytes now versus like before, which was just like a couple 10 gigabytes. And here's kind of like a chart that shows you like the cost. So does Ethereum face the same problem? Yes. Short answer is yes. And this is the marvelous CryptoKitties, which I think made this issue kind of mainstream, which really brought the attention to everyone to start kind of working on this problem. And that's why a lot of people in the Ethereum Foundation are just going harder than ever on scaling solutions and getting other people to start writing their own scaling solutions. So right now Ethereum is stuck at 15 transactions per second. You have CryptoKitties that are slowing down the network and causing gas to increase. And the limitation here is that we understand that the computation done on Ethereum is redundantly parallel. And this is basically by design because this is what makes blockchains authoritative and secure. People being able to verify that you ran this code is only verifiable by running the code itself. Now, if you had really good static analysis, like how we discussed in the last lecture, like Solidity has pretty bad static analysis, so you can't really tell what's going to happen before the code is executed. If you have really good static analysis, then you can say, oh, I know what's going to happen from just looking at what tokens I absorbed from reading the code itself. Now I can say this is going to be the output of that. And that doesn't require me to like run, that doesn't require me to run the program itself. So it's not as resource extensive. Yeah?
So are there people working on scaling solutions for using static analysis tools as a scaling solution?
Yeah, I believe so. I think part of eWASM's effort is to do that. But yeah, it's kind of more in the lines of they have to make things more formally verifiable, and I think that's a pretty tough problem. But it's also not my area of expertise, so yeah.
You said that with static analysis, you could look at it and see that yeah, this would be the answer. Is that verifying an answer or getting?
I guess verifying the execution,
Okay.
not necessarily the answers.
Okay.
Yeah. That has to do more with like you can do like formal math proofs on like certain code. I'm not like a Haskell programmer or anything, so I'm not familiar with it, but I've seen stuff that does that. Yeah. Any other questions? Cool. So yeah, this basically is the limiting factor. Redundantly parallel execution requires that we take into account the individual nodes in the network, and we have to think of them as the limiting factor because the transaction output can't be higher than what we are willing to require computationally from a single Ethereum node. So how do we fix this? We could ask every individual node to do more work in some respect. We could double the block size. We could roughly get double the amount of work being processed from each proof of work, from each epoch of each block, essentially. But this comes as the cost of decentralization. You're basically limiting people from joining this network because people in third world countries won't be able to keep up. in order to like operate well in a third world country, you need someone to run like full nodes there, so that the latency can actually participate and compete in the Bitcoin network itself. So that actually does destroy decentralization. And if everything's centralized, blockchains are pretty much like not as useful. So we need to find a way to increase this workload with basically on the overall blockchain, but without increasing the individual workload on all the individual machines. Oh. Yeah, so we can look at a few ways to do this. One way is to start by looking at networking scaling. So you can think of Bitcoin's network as being bottlenecked at the packet transmission level. This is kind of ignoring like the consensus drawbacks of proof of work, because you're basically sending transaction twice. That's once for the originating transaction, and then one for when it's included in the block. So when somebody submits a transaction to the network, basically like they send the transaction to everyone. Everybody gets that transaction. The full nodes receive that transaction. They put together a block. They basically put all those transactions in the block. They send those transactions out again through that block. So there's some redundancy there. So one way to fix this is you can have miners get transactions they don't have from new blocks, and they can essentially reconcile them with their own set. Kind of confusing, but think about that. Another thing is dynamic P2P systems are pretty difficult to build for. There's this thing known as expander graphs. I won't go into these, but basically they are graphs with a high amount of neighbors per subset. And there are basically low diameters between nodes in this graph, means reduced transmission times between any neighbors. So this reduces the need to revalidate every transaction if neighbors are trusted. And you can also optimize random peer selection in order to get away from eclipse attacks, and also denial of service attacks. And rate limiting is also an option. Do people kind of remember how the eclipse attack works? Does anybody want like a mini recap? Okay. So in the eclipse attack, so if you remember dev P2P, people connect to the DHT. The DHT has like some set of public keys linked to Ethereum nodes that are on the network that you can go to and you can fetch block data from. It also is a way to discover other peers in the network, not only just for downloading the full chain, but also for just broadcasting to people in general. So in order to eclipse people, any ideas what people will have to do in order to eclipse people? What might they have to do to the DHT? Yeah.
You're just going to have to change pretty much for that specific node, like every connection that comes in, you have to like modify that connection for that one person.
Every connection. Can you repeat that?
So like, from what I understand, it's like you have like one specific node that's trying to like connect to the network, but then for each request that goes out, you send back a same false request to that person, and so they have a certain idea of what the network is that isn't actually, because they never actually fully connect to it, and that's you cut it off.
Not quite. So I think you're on the right track. Here's what I think will build more intuition. So if you remember Kademlia, Kademlia has like Kademlia makes it easy for you to like find neighbors via like its distance metric. You can basically like hop to other branches in that binary tree very easily using the distance metric. So how do people kind of exploit that distance metric? Well, the most recent exploit that was performed was some guy would just continually generate public-private key pairs. They would just keep bringing up new Ethereum nodes, and these would be like malicious nodes. And by generating more and more key pairs, that's what Kademlia's distance is actually like based on. So using that, you can essentially perform an eclipse attack because you can basically make it so that their nearest neighbors, the nearest neighbors of a certain node, end up being eclipsed via the distance metric itself, because the distance metric is based on those public keys. A lot to wrap your head around. I'd recommend, there's a paper out there on this that was released in March. If you talk to me afterward, I can give you the links. So back to network scaling. One of the fundamental problems is that nobody is incentivized to propagate blocks. And this mostly relies on voluntary participation because people propagating blocks are full nodes, and full nodes don't get paid. People who do get paid are miners. Also, there are no disincentives against continual propagation. So you don't punish people for like trying to push more blocks than they should, or just like spamming like multiple nodes on the network. So if you had enough power, theoretically, you could like try to take down the Bitcoin network but it would take a lot because taking down a distributed peer-to-peer network is very, very difficult. There's also consensus scaling. I think most of you are probably more familiar with this type of scaling. So the idea is we need to designate some accepted set of transactions for consensus scaling. And basically this plane, the consensus plane itself, it's essentially absorbing all messages from the network plane, and it's outputting all the transactions for insertion into the system itself that someone's running on their node. So this is the one that mines blocks, and it reaches consensus on their integration in the blockchain. So this is actually artificially bottlenecked because it's mainly the network plane that's the main bottleneck, right? And actually, could somebody think of why this is the case? Because if you think of Bitcoin's, I'll give you a hint. If you think of Bitcoin's network difficulty, or sorry, block difficulty, why is Bitcoin difficult, right? Can anybody like maybe propose an idea as to why Bitcoin has such a difficult puzzle it needs to perform? It comes down to like network latency. Okay.
Well, if it weren't difficult, then you'd get lots of people validating transactions and making blocks all at once, I guess.
Yeah, actually, you're right. Forking is a big part of it, and it also has to do with latency. You kind of want to set the playing field right. If you have enough difficulty, and the block time isn't so like ridiculously quick, there is enough time for other people with essentially less latency advantage to propagate their block. At the same time, you also have to think about where people are like globally located, and you can think that because say all the miners are in China, you can say that the people in China have an advantage latency-wise because they're closer to the miners. So consensus scaling, we know proof of work. We saw Ghost Protocol. We saw how it makes for quicker block times and incentivizes people to create uncles, find like similar blocks, and still get rewarded for it. Another consensus algorithm that we haven't quite covered is proof of stake. I won't be covering it today, but essentially the basic idea is that you have validators in the network, and validators are crypto-economically basically insured to be honest. So what that means is they are rewarded for submitting honest blocks, and they are punished for submitting like invalid blocks. And people who catch these other people are essentially rewarded the punishment fee. There's also Consortium Consensus, which is essentially a private blockchain where people just use like some BFT protocol, but if you don't use sharding and you want to scale like this consortium protocol to a pretty large scale, then it's still like it still suffers. Then there's sharding. I'll talk more about this later, but this is often used with centralized databases as well. And basically, all it's saying is let's split up the task among our nodes, and then let's come to consensus securely among all those tasks that are happening essentially concurrently. There's also sidechains. Sidechains, I will talk about. I'll talk about a specific example, which is Plasma. Plasma is essentially a sidechain. So we'll talk about that later. Yeah. So storage scaling. So again, the 4 days. Is there any way that we can possibly make this more secure or more compact? One alternative storage model is that someone came up with this idea of UTXO data sharding. It's basically like you send parent transactions along with their Merkle branches, and you essentially have proof that that transaction occurred, and you just worry about the transactions that are most relevant to you. So you can be very selective. You can be very selective about which transactions you choose to look at. The only issue with this is that this scheme is actually not quite safe, but we'll see in the case of sidechains that something has actually been proposed that is somewhat safe. And if you don't know what I'm talking about, that's okay too. I will explain everything in later slides. Yeah, view scaling, basically the view plane, it's basically the interface that abstracts away from the chain's entire state and only focuses on relevant information. So the UTXO set, for example, or the contracts that are involved in Ethereum inside a new transaction versus every contract. And the view may also be stored in storage as an optimization. This is kind of like pretty minor, to be honest. So let's skip this and talk about sharding. So what if we could have a blockchain? What if we could have a blockchain where every node didn't have to process every single transaction? What if the network was divided into 2 sections, and those 2 sections could operate independently? Section A could then be processing one batch of transactions. Section B does another batch, and at the end of the day, they come to consensus somehow on this entire batch, and they put it together, and you basically multiplied how much scaling you've achieved. This seems pretty simple, but when you start to think about how consensus gets involved with sharding, it becomes a pretty difficult problem, and that's why it hasn't been implemented yet. That brings me on to talk about the different forms of scaling. Layer 1, we just talked about sharding, and we talked about all the different ways you can adjust the network plane, the consensus plane. This is basically adjusting the base protocol of Ethereum such that you scale it, and this is focusing solely on the main chain. This also requires a hard fork to implement, so there is a lot of overhead. It's not that simple. Layer 2 is not necessarily simple either, but it's definitely more easier to deploy, and you essentially delegate more trust to certain endpoints. And layer 2 also just says, what if we could do more things with the capacity that we already have? We could say that the main chain ends up being the same. We leave the main chain alone. We say, okay, let's create this new abstraction that communicates with main chain and starts doing things off chain and starts to secure things there and does its verifications there, but then leverages the main chain when necessary. So in Ethereum, in the case of Ethereum, we're running things on smart contracts actually. And the crazy thing is, you never think that you could actually just start scaling with these things, right? Because smart contracts seem kind of limited. They seem pretty stupid, but you can scale with them, and I'll show you how. So I'm going to let you guys sign in. Did everybody get the sign in? All right, cool. Let's talk about layer 2 scaling in depth now. Let's see how this thing is actually implemented. So we know that much of the power in public blockchains relies on crypto-economic consensus. That means by carefully aligning the incentives in the network and securing them with software and cryptography, we can create networks of computers that reliably come to some kind of agreement about the internal state of a system, right? What that basically means is blockchains are this finite state transition machine that incentivizes people to keep it valid and make it Byzantine fault tolerant. So crypto-economic consensus also gives a strong guarantee of security. It gives you this, you can think of it as this core kernel of certainty. And this is an important idea, I think, for sidechains or any layer 2 solutions that you start to think about, and you'll see why. But unless any like 51% attack happens, we can assume that it's secure. So we'll trust that the main chain is running as it should. So we'll use that main chain as this anchor for finality, right? We'll always be able to look back at it and say, this is truly the secure chain. We trust it. We assume that it works. Layer 2, then we'll say we can then have any transactions that are off the blockchain that will, go back and refer to it if things go wrong. And this will be, again, this will be a very important mechanism. But the layers built on top of Ethereum, the reason why we need to refer back to the main chain is because you won't always have the same guarantees. They can still be like pretty close to final, and they can still be pretty secure to be useful, but there's this slight decrease in finality, and this is a good trade-off though, because you can basically increase your throughput like crazy. You can stop publishing transactions on this 10 transactions per second main chain, and you can say, let's just look at the end state of things. State channels are the first way to do this, and I think they're the simpler solution. You can actually write this in a smart contract. Probably something we'll do next semester, or maybe introduce for lab next week. We'll see. So this is a technique for performing transactions and other state updates off-chain. Things that happen inside will still retain some degree of finality and security. And if things go wrong, we have the option of referring back to the anchor in the main chain. And payment channels have been around for quite a while. If you've heard of the Lightning Network, that's been like a project that's been going on like forever, honestly. It's been going on for years. I think before Ethereum's existence, it's been going on. State channels are then the generalized version of the payment channels. And you can basically use this for any arbitrary state update. So rather than just sending coins to like Alice, between Alice and Bob, I can now start running different smart contract executions. Like I can play out a whole chess game with a friend and then submit the final state on chain. And that result will be much faster than waiting for every single step in the chess game to be essentially confirmed on chain. Now you do sacrifice some degree of finality here, but there is ways to kind of secure it so that you don't get screwed over. But there isn't necessarily a way to ensure that everybody's online, and we'll see that availability is essentially a problem here. So you can't ensure completion of things. So let's assume that Alice and Bob want to play tic-tac-toe, and this is a contract where the winner receives 1 Ether. The naive implementation is that you create this contract on Ethereum. It keeps track of all the players' moves, and every time a player wants to make a move, they send a transaction to the contract. And when one player wins, as determined by the rules, right? Tic-tac-toe is pretty simple. You just look for like some like set of symbols like lined up, right? So the entire Ethereum network is processing this game. It's redundantly parallel, which sucks. They have to pay gas costs every time a player wants to make a move and wait for blocks to be mined before making the next move. Seems pretty bad for like tic-tac-toe. Like you're taking up like one of the world's like most massive supercomputers, and you're basically running tic-tac-toe in a block, and you're wasting resources that could probably be used for more important outcomes. So let's create a smart contract called Judge, and this will be on the Ethereum main chain, and this understands the rules of tic-tac-toe, and it can identify Alice and Bob as the two players in the game, and it holds the 1 ETH prize, so it manages who gets the prize. So you're essentially trusting that this judge is doing the right thing, and there's ways to ensure that it is doing the right thing, and we'll see. So Alice and Bob start playing the game. Alice creates and signs a transaction describing her first move, sends it to Bob, who also signs it, and then sends back the signed version, and then keeps a copy for himself. So they basically just did it back and forth. Then Bob creates and signs a transaction describing his first move, sends it to Alice, who also signs it, sends it back, and keeps a copy. So both of them are basically keeping track of the state between each other, and the two of them are essentially, you can think of it this way, the two of them are essentially coming to agreement on what they did. And they are going to agree at the end that to be honest, right? So you might be thinking, wait a minute, what happens if one of these people just decide they realize they're going to inevitably lose in tic-tac-toe, right? They choose not to make like a move because they get in the trapped like scenario where like no matter which move they make, they're game over, and they decide to stop playing, right? Let's say they do that. What could be a way to incentivize people to go on and until the execution of the state channel is over? What could be an incentive? And remember, we have a judge contract here. What could be the incentive? Yeah.
You both put something in the judge as well, so instead of just putting the 1 Ethereum gets the price, you both also put some collateral that you will be given back once it ends.
Yeah, that's definitely a really good way of doing it. Just basically put some collateral in the judge contract, such that if any of the players decide to mess up or say, I'm not going to participate, well, then they just forfeited the collateral, and they can't get the reward at the end of the day. So this is like a crypto economic security way of doing things. You make people pay up, and then it's pretty cool to see it happen because like you're just doing like basic business logic in like a blockchain. So not usually done in computation like this. Also, one thing to note is that as they update the current state of the game between them, somebody can kind of like see like what step of the game they're at, because every transaction will contain a nonce, so we can always tell like later on what order the moves occurred. So Alice and Bob are simply sending transactions to each other over the internet, but nothing has hit the blockchain yet. So all the transactions could be sent to the judge contract, because they are valid Ethereum transactions. And you can also picture this as two people writing a series of blockchain certified like checks back and forth to each other, right? They're just sending money back and forth between each other, saying, okay, this is the state, this is the state, we agree. So nothing has been like concluded. But they can also like choose to deposit whenever they want. And in the case of tic-tac-toe, you might not want that to happen. You don't want them to be able to deposit whenever they want, because then they would be quitting the game, and that would be defeating the purpose. You might want to punish them if they decide if they try to like deposit, right? If they try to exit the state channel. So when Alice and Bob are done playing the game, and this is perhaps because Alice has won, they can close this channel by submitting the final state to the judge contract, and they only pay a single transaction fee, and the judge will then ensure that, okay, these transactions have been signed by both parties. It'll wait a period of time for the two parties to kind of challenge the result, and once that's over, once that challenge period is over, it'll pay out the 1 ETH to Alice. So why do we need this challenge period where the judge contract waits? So imagine you send the real final state to the judge. Instead of doing that, you send Bob sends an old version of the state, one where he's basically winning ahead of Alice. And the judge is just some stupid contract. It doesn't know how to read the states. It doesn't know what to do in that case. So the challenge period will give Alice a chance to prove that Bob basically lied, and the judge can actually reward Alice in the case that this happens, or punish Bob, whatever it wants to do. And if there is a more recent state, she will then have a copy of the signed transactions, and then she can submit those to the judge. And basically, the judge can tell that Alice's version is more recent by looking at that nonce, and Bob's attempt to steal the win is rejected. So there's all these ways that you can kind of check that somebody tampered with your state channel transactions. And remember, this is all between smart contracts, which is a little crazy. So some features and some limitations. One of the things is state channels really rely on availability. If one of the people go offline, what do you do in that case? It's useful when participants are going to be exchanging a lot of state changes with each other over a long period of time. And it's especially useful when you know who those people are. Also, state channels have very strong privacy properties. And this is because everything just happens between the two participants in the channel. And you might not know what exactly happened between those two participants. You just know the end result that happens on the main chain. And this is just essentially secured by what goes on between the two people in the smart contract. It is essentially off-chain. And state channels also have instant finality. So as soon as both parties sign a state update, it can be considered final. You can basically verify that these are valid states because the parties agreed on it. These are some implementations of state channels that you can kind of look more up on. There's Counterfactual, which I recommend, Funfair, which has pretty good stuff, Spank Chain, which I spelled wrong, but that's a very focused use case. But they do write good code. Let's talk about Plasma. So like state channels, Plasma is this technique for conducting off-chain transactions while relying on the underlying Ethereum blockchain to ground its security. But Plasma takes this idea in a new direction. It allows for this creation of child blockchains rather than just this state channel where we just send each other transactions between a defined set of participants. So these child chains can spawn their own child chains, who can spawn more child chains, and so on. Essentially, if you look at some implementations of Plasma, you'll see that they're just smart contracts with a basic blockchain written inside of them. That's what you can think of a sidechain as. And it has all the Merkle proofs. It has all the ways that you can basically operate on a blockchain, except it's in a very compact format. And what this does is this allows us to also run very complex applications as a result. In some cases, more complex than state channels. So let's suppose we're creating some kind of trading card game on Ethereum. The cards will be ERC 721 non-fungible tokens like CryptoKitties or something like that. And they have certain features that let users play against each other, like in Hearthstone or Magic the Gathering. And these kinds of complex operations, you'll realize, are pretty expensive to do on chain. So you decide to use Plasma instead for your application, because you don't want to be doing a ton of card state changes on chain. You don't want to be updating the game state for so many games on chain, because your users are going to get pretty pissed. So first, we create a set of smart contracts on the Ethereum main chain that serve as the root of our Plasma child chain. The Plasma root then contains these basic state transition rules of our child chain, such as transactions cannot like spend assets that have already been spent, so just no double spending. There's other properties which we'll kind of go into a little more rigorously later. The plasma also records hashes of the child chain state. It serves as this bridge that basically lets users move assets between the Ethereum main chain and the child chain. Then we create our child chain. This can have its own consensus algorithm, and let's say that it basically uses proof of authority because we want to use like a simple example. If you imagine like writing a proof of work blockchain on like Solidity contracts, you can imagine that gets a lot messier than just dealing with saying that, okay, this person's the block proposer, they're in charge, hence proof of authority. So let's keep our example simple. So once the child chain is created and active, the block producers will then make periodic commits to the root contract. This means they are effectively saying, I commit that the most recent block in the child chain is X, right? The block producer is also going to be called the operator in Plasma. We'll kind of like dive into that a little more. And basically these commitments are going to be recorded on chain in the Plasma root as proof of what has happened in the child chain. So basically all we've done so far is we've created a peg in the main chain, and we've created a initial block in the Plasma chain, and we've kind of just connected the two via like a smart contract that runs Plasma. So now that the child chain is ready, we can now create the basic components of our trading card game. The cards themselves are ERC-721s. These are created on Ethereum's main chain, and they are moved onto the child chain through Plasma's root. So this introduces some crucial points. Plasma lets us scale interactions with blockchain-based digital assets, but those assets should be first created on the Ethereum main chain. Then we deploy the actual game application smart contracts on the child chain, which contain all the game logic and rules. So does it make sense why we should be creating those assets first on the Ethereum main chain, based on like the properties that we kind of learned about just sidechains in general and Plasma? Okay, not to worry. We'll cover that again. And then when a user wants to play our card game, they're only interacting with the child chain. They can hold assets such as the ERC-721 cards, right? And they can buy and trade them for Ether, play rounds of the game against other users, and they can do all this stuff without ever interacting with the main chain. Like never have to touch it. And because only a much smaller number of nodes, the block producers have to process the transactions, the fees can be much lower and all the operations will be much, much quicker. So we basically just delegated all the work down to that child chain. Now, how is this even safe? Like, why is this even like give us any guarantees of safety? So we know that so far that we can move operations off the main chain into a child chain to perform more operations, but are all these transactions on the child chain, are they considered final? And also, isn't proof of authority pretty lame because there's a single entity controlling block production on the child chain, and isn't this all pretty centralized, right? Can't the company then like steal your funds if this is like completely centralized? Like if they're basically running the Plasma contract, and they have access to the Plasma operator, can't they just steal all your funds, right? So even in a scenario where a single entity decides to control 100% of block production on a child chain, Plasma gives you this basic guarantee that you can always withdraw your funds and assets back onto the main chain. And if a block producer starts acting maliciously in some respect, you can basically exit the Plasma chain. Pretty smart way to solve this issue. Plasma also has incentivized fraud proofs to prevent cheating and reward those who catch it. So if somebody tries to, if a operator decides, hey, I'm going to try to, take your money basically because I have your transactions, I have your signatures for those transactions, I have like the ordering for those. I can just reorder them and not use some of them and use others, and I can try to publish those in a block onto the main chain, right? I can try doing that. But because Plasma has fraud proofs, and it also has the time to basically check at the end. It has a challenge period, right? You can basically have people who are in the Plasma chain basically contest this, and by contesting this, they get a reward for doing so. So you incentivize people to fight the operator in case they try to be dishonest. Now, user experience-wise, this might be a little tricky because you have to expect the client to do something about this. But it's certainly possible to secure it, is the point. Also, censorship resistance is pretty much lost in this case, though. So that's something we do have to accept. Like if the proof of authority guide just chooses not to accept your, they choose not to accept your transactions as once you join this Plasma chain. I guess the only choice you have is just to exit and just work on another Plasma chain. So censorship resistance is kind of a downfall of this proof of authority scenario. But you also might be concerned about what about if everybody decides to exit/withdraw, right? If everybody tried to withdraw at the same time, there might not be enough capacity to do so on the Ethereum main chain to process all these transactions within the challenge period, right? So users could potentially lose funds. And there's this whole thing about availability where users need to be basically active in order to ensure that they are responsible for their own funds. If things go wrong, they basically need to be looking out for that and contesting that on their own time, which isn't great, but hey, it scales. And if you write a good client, I think it could work. Also, there are many possible techniques for preventing this. You could just extend the challenge period in a way that is just responsive for the demand for withdrawals. So if you have a mass withdrawal / a mass exit, which are same thing, right? Exit, withdrawal, same thing. If you have those, you can basically just adjust. You can just adjust the challenge period time. So it's worth noting that you don't have to use proof of authority. Like I said, you can definitely try to implement some other type of consensus that is much more secure and is pretty much decentralized, similar to how public blockchains are. In those cases, there are less risks that the block producers would be able to interfere in the ways we just described. So therefore, a user would not have to move their assets. They wouldn't have to exit. So there's less risk in general for everyone. So let's do a comparison. I think looking at state channels and seeing how Plasma compares. State channels, definitely faster. So they can perform instant withdrawals when all the parties in the channel consent to withdrawal. So if Alice and Bob agree to close out of channel and withdraw their funds, as long as they agree to that final state, they can get their assets out of the channel immediately. On Plasma, the users always have to go through a withdrawal process, which involves a challenge period. State channels should also be less expensive per transaction than Plasma, and they will be faster. You've already seen that they're just much more lightweight in architecture, and I'm about to show you what Plasma's architecture looks like, so that'll be interesting. So if you had an example, where two users are exchanging some series of small transactions, this would be a case where you can use Plasma and state channels together. You can combine the two because essentially state channels is just an abstraction under blockchains, and Plasma is basically very close to how a blockchain works. So you can just run, if you can run more Plasmas under Plasma, you can basically run more state channels under Plasma itself. So minimum viable Plasma is what a lot of people are working towards right now. It's basically what the research is focused on, and people are trying to get a minimum viable version of this. So that includes just putting the constraints lower and just making it ideal circumstances. So the idea behind minimum viable Plasma is the Plasma chain should be as secure as the root chain, which is why we can have a single operator which basically is the same as the block proposer. And because it's a constrained authority with using proof of authority consensus. We should also have these security guarantees, such as tokens not being able to be double spent, they cannot be withheld, and tokens can always be redeemed on the root chain. So people should be able to exit whenever things are about to go wrong and immediately just say, I'm going to go back to the root chain. See you later, Plasma chain. So Plasma exit again, that's how you pull coins off the main chain. And there's a lot of terminology here, so I encourage you to kind of like review, and I'll be posting like a lot of readings on this because there's a lot of good ones out there. So Plasma is coded on a smart contract on the root chain, as we've said, and this is deployed on mainnet Ethereum, and then you have all your abstractions below it. The MVP is basically designed for token transfers. It can be designed for ERC 721, general state transitions, etc. And the MVP, we know that it uses proof of authority, so that's great. And I want to thank Carl Florsch for his explanations, because he actually explained it really well, and he gave a really good idea as to how to look at Plasma. So here are some functions that I'm going to run through. So this is where the operator decides to create a block, right? So we start off here where we have the main chain, we have the Plasma chain. Plasma chain isn't really started yet, but we have a Plasma contract that is going to be deployed on the main chain. It manages Plasma blocks, and that exists. Those Plasma blocks are going to exist in the Plasma operators database. You can think of the Plasma operator as some abstraction within the Plasma contract, and it's basically able to make decisions about which blocks get proposed to the main chain. So the operator then creates a block, and this is a Plasma block inside the operator's database, and this is not included in the main chain just yet. The operator then sends a transaction to create the initial Plasma block, which contains the Merkle root of transactions and state to the main chain. And the miner receives it and then creates a block on the main chain. So that block is now confirmed, and the Plasma chain then gets confirmed once it is on the main chain. And that's pretty much it. So that's how you get the Plasma chain up and running. You basically just deploy the contract. It does some back and forth interactions. It then confirms on the main chain. Once confirmed on the main chain, and once you know, when you deploy a Plasma contract, you generally know what states you might want to start with. When you start a Plasma chain, so you might pull over the initial states and start those states in the initial Plasma chain block. And that state needs to be basically just confirmed by looking at on the main chain. So let's start with another example. This is where just some guy Sam just decides, I'm going to deposit some ether into the the Plasma chain. So Sam then deposits some ETH, which is immediately going to create a block on the main chain. So no interaction with the Plasma chain just yet. The block on the main chain then is basically confirmed. It says that Sam has whatever ETH he's deposited. So nothing has happened on the Plasma chain yet. So then the Plasma operator then syncs with the main chain, and that's free of cost because the ETH network basically took care of it. They did the consensus to verify that Sam put in the ETH. Everything is good. Sam now has 5 ETH, but then also now he has 5 Plasma ETH. So Plasma essentially just created its own abstraction of how much ETH that Sam has. And also, when you do this, basically, it can basically automatically confirm that on the Plasma chain, Sam has 5 Plasma ETH, because it's already been confirmed on the main chain that he has 5 ETH. So we can just say that he has 5 ETH on the Plasma chain as well. So now Sam is going to watch both the main chain and the Plasma chain, and he's going to look for misbehavior on the Plasma chain. But also, he's also going to look for, he's not going to look for misbehavior on the main chain, because the main chain is basically the thing that you look up to. It's the thing that you trust. You can think of it as a trusted computing base, in this case, a TCB. Yeah.
When the ether gets transferred in doesn't really. When he gets those 5 plasma ether, does that somehow lock down those original 5 ethers so that those can't be used elsewhere?
Good question. It does, yeah. It's kind of like how, I can't really use like the proof of stake example, but basically like Sam is basically like staking it for like this plasma chain, and he's saying that I'm putting up this much ETH. Now Sam could like exit early on, and he could say I'm not gonna like deal with plasma. Could he try to double spend? The answer is no, because the plasma operator would be able to like see it. Yeah. Okay, so the next step is Sam sends a bunch of transactions to Alice. Okay, so basically Sam tells the plasma contract, Sam tells the plasma contract, I'm sending Alice 2 plasma ether, and the plasma contract goes to the operator. The operator then says, okay, I'm going to include this transaction inside my next plasma chain block. And note that the block has not been confirmed yet because it's not on the main chain, and then until it is on the main chain, it hasn't been confirmed. So as we see, Sam has 5 ETH, 5 P ETH, Alice has 2 ETH, 2 P ETH. The block will then be submitted onto the main chain by the operator, and it needs to be confirmed, so the balances are still the same. Notice that Sam is still watching for changes. Sam will notice that Sam will basically notice the 2 chains, and he'll notice that his transactions were included. So this is assuming that the main chain confirmed that most recent block here, and basically Sam sees that it's been confirmed. So he now knows that the transactions were therefore included. So Sam then sends a confirm message to Alice acknowledging that his transaction was in the main chain. And then the balance update. So Alice can therefore spend those coins. So yeah, now the plasma chain is confirmed. Sam attempts to exit with all 5 PETH but fails. Yeah, so unfortunately I don't have graphics for this, but I'll walk through it nonetheless as best as I can. Ask questions, feel free. So basically Sam is going to submit an exit transaction to the main chain, and this is basically the final arbiter that keeps everyone in line. And you have to remember that Sam no longer has these coins in this scenario. Remember that he is attempting to withdraw all 5 PETH, but remember he only has 3, so he doesn't have all those coins. So he sent a few of them to Alice. So since he doesn't have this balance, when he tries to exit with 5 PETH, the exit is going to have a challenge period. And basically, if the exit is invalid, the main chain accepting any transaction, the main chain is basically accepting any transaction from it's accepting any transaction from anyone to say that you can challenge this, and anybody who decides to challenge it will then receive some kind of security deposit bond. That's basically a bounty for securing the system. Alice can then basically send the challenge. She can basically send the challenge before the challenge period ends, and she's going to send it. She's going to send the challenge by sending a Merkle proof of the transaction tree and the state tree showing that Sam has already spent the coins. This guy does not have 5 ETH. He's clearly spent 2 of that ETH and he's given it to me. Therefore, he is trying to double spend. So Sam's exit is invalid, and therefore this will cancel Sam's exit. And then Alice is going to get paid a security deposit, and Alice is a happy person now because she has more ETH. The final example I would like to go through is where the operator decides to create an invalid block and all the users just exit. So the operator basically just tries to print money by creating an invalid block, and this is perhaps by just stealing from the users because they get all the transactions, and by basically getting all the permission to submit transactions, the operator can just start to rearrange things and say that basically I have this balance. I can just increase my balance by using the money that other people put inside my plasma contract. And basically, the plasma operator can then try to exit and steal all the plasma ETH. The clients notice the bad behavior before their money gets stolen, and then they hopefully like submit a challenge. And when they do try to like submit, like a challenge, basically this is actually going to come. This is going to come first because the Plasma operator has created a new transaction saying that I basically own all the balances that I guess are inside the Plasma contract or inside my database or whatever. And that's a newer transaction, right? That's newer than the previous transactions saying that, hey, Alice has like 7 ETH and Bob has like 5 ETH and whatever. It's basically the original transactions will be prioritized in the challenge queue. So because of that, the operator will lose in this case. So here's some concluding thoughts about Plasma. So there's some issues. Basically, it is the responsibility of everyone holding value on the sidechain to notice if something goes wrong, and that's very bad for user experience. There could also be congestion if everybody tried to exit at the same time, and this would be very bad if there was an ICO happening at the same time. So it could be a little difficult to extend the challenge period to an optimal length. Also, the ultimate finality is dependent on the main chain, so you better hope that the 51% attack never happens. But then again, all this thing just like goes to crap if it does. And in the proof of authority network, you do need to trust the authorities. Also, tooling can kind of be an issue, but there is going to be a block explorer coming out soon, which is nice. So then you'll be able to see like the different transactions that have happened on Plasma, which would be pretty neat for developers. And also, you can't offer transfers as quickly as state channels do, although you can allow for many-to-many transactions with Plasma. So we have some constraints in general, just that we've kind of gone over, and I think this is a good way to tie it up. Basically, we're trying to scale blockchains without trying to lose decentralization, and we're using deposits to constrain the bad actors. Trust is also just established by limiting possible actions and imposing any costs for these bad behaviors. And we try to store minimal information on chain. And Plasma basically is doing this by avoiding any storage of intermediate state, and it just takes care of the endpoints. It just looks at the incoming and outgoing balances. So yeah, that's all I had for you guys today. We'll see you next time. Next time we're going to be in lab. It's going to be a lab with Max, who's the guest lecturer. He's from Lightning. And we're going to have Howard Wu on Friday. He's going to be talking about ZK snarks and lip snark, which is like his research. So we got some cool stuff coming up. Yeah, thanks for sticking around, guys.